Oh, I'm sorry. I interrupted. Welcome to Honors Physics Lesson 5.1, Projectiles. All right, so here is what we got. So a projectile is anything that is in free fall. We've already kind of done free fall, but now what we're dealing with is something that is in free fall. It also has this weird horizontal component. It's moving over as well as up and down. So if you throw a ball up in the air, you have the force of gravity acting on it, which gives it that direction, it gives it that curved path. And it also has this change in speed. So its speed slows down while it's going up and then speeds up when it's coming down. So if you remember this as a vector quantity, that'll make this a whole lot easier. Because there are two big rules of projectiles. And the first rule is horizontal velocity of any projectile will always remain constant. The moment that a projectile leaves without applying that force is no longer in contact, so it will keep doing whatever it is doing unless another force acts upon it. I wonder if that is Newton's first law, which means that there is nothing to accelerate it horizontally. That means that the horizontal velocity remains constant. Remember, gravity only pulls things down. It's not going to pull things to the right or to the left, unless, of course, right and left is down. So take a look at this. Here we have a car. It's not a sweet Mustang, but it will do. It is going off of this cliff in that direction. Gravity pulls, different color, in this direction. So if it was going 20 meters per second that way, then after 4 seconds, even though it'll be, I don't know, down here somewhere, it's still moving at 20 meters per second. So if it's in the air for 4 seconds, that means that the velocity equals delta x over t. So, in other words, 20 times 4. That's how far away it'll be. Now, as far as the initial velocity going down, and this is what always causes a little bit of confusion, the velocity initial going down is actually 0. Because this velocity is horizontal, and this velocity is vertical, or Vy and Vx. Oh, that's fun. All right, so now let's look at big rule number 2. A projectile vertically will still have the same acceleration as anything else that is falling down, regardless of how fast it's going horizontally. So if we look back over here, even though it's moving 20 meters per second that way, acceleration of gravity is only pulling it down, so it'll still have that same acceleration of gravity down, which is that negative 9.8. F equals ma. That means for every second, the vertical velocity will decrease by 9.8. In other words, the speed should be going down, right? Everything's going down. Everything's falling down as long as we disregard air resistance. All right, so take a quick reference here. Let's say we have 6 cars, and they all go off a 44-meter cliff. Which one hits the ground first? Car A, car B, C, D, E, or F. They all have different horizontal velocities. Well, this is kind of a trick question because they're all going to hit the ground at the same time. It doesn't matter what their horizontal velocity is. If they're all going off the same distance, vertically, they're all going to hit the ground at the same time because gravity affects them all the same. All right, so if we look at a cannonball, and this cannonball is being launched horizontally at 58.8 meters per second, then this is our initial right here. Vx is 58. We have no Vy, right? We haven't put on any angle. It's being launched horizontally. So it would look like this. Horizontally. We're given 58.8, and it keeps going down. Now, after it goes off of this ledge or wherever it's going down to, however it leaves this cannonball, then gravity starts to pick it up, and it starts to go down, 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 down every second that it falls. Now, the only thing that they will have in common, that was weird, is time. Time is going to be the same no matter what. So it's moving over the same time that it's moving down. All right, so now let's take a look at a projectile that's being launched at an angle. So a projectile that's being launched at an angle, such as so, has two components. It has whatever the overall velocity is, which is normally given to you as, oh, a cannonball or a car is being launched at this velocity. And then from there, there's two other velocities. There's your x component, which will always be constant, and then there's your y component, which decreases as you go up and increases as you go down. Well, whatever. Grammar is not my forte today. The way we're going to look at this is for this x component right here, we can go ahead and take our cosine of our angle, since that's our adjacent side, multiply it by what our overall velocity is, and that will give us the x. This will remain constant, so this will never change. Notice here, they're all the same. Now, as you go up the y component, that one is going to be the sine of whatever our angle is times v equals vy. This one will change. This one's being affected by gravity. Gravity is pulling it down, so our y velocity will change. It'll decrease till it reaches 0, and then it'll increase in the negative direction or decrease, depending on how you want to look at it, all the way going down. Some equations that you're going to want to look at. Any part for horizontal, we're going to look at that. Here are vertical equations. This is anything that's going for our vy. This helps us with our angle, so opposite over adjacent. This is tangent. For SOHCAHTOA, for those of you who don't remember or don't apply it. And then we have the Pythagorean theorem. Shout out to you, Mr. Martin, Pythagorean theorem. This is going to help us find our overall velocity. So we'll take the squares of those two components to see what our overall velocity is. All right, so let's take a look here. I'm already running low on time, so I'll just give you a quick tutorial here. So here's our initials. And here are our answers. Notice that the x value doesn't change, the y value does. Angle. This is at the top, so where y velocity is now 0. As it comes back down, it starts becoming below the horizontal. So this is all above the horizontal. Now this is all below. And then here's our delta x, which is going by this multiplied by time. And then our delta y. As it goes all the way back down to the ground. Again, make sure that you are finding your components. So if we launch a ball at this 58.8, that is not the x value. The x value will equal the cosine of whatever our angle is, 30 degrees, times 58.8. That'll give us our Vx. Our Vy will give you sine of 30 times 58.8. And those will give us our initial velocities. This one won't change. That's why this is all 50.9. Doesn't change. Our y decreases by a negative 9.8. It goes down until it reaches 0. So as it's going through its path, it goes up, 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 comes to a point where it can no longer go up, and then starts coming back down. That's what this is showing right here. So this 3-second part on this problem is very important because that is the top of our path. The angle should decrease until it gets to 0 as it goes up, and then it goes below the horizontal. Delta x, you're always moving forward. Delta y, it's you're going up, 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 up until you come back down. All right, we'll call it there. I know it's a little bit longer, a whole 10 minutes, so we'll pick it up next time with circular motion. Oh, look at that cute doggy. Okay, talk to you later. Goodbye.